So we started at 13. So can everybody do this? Put this in your L1. Stop me if you can't. You can put this in your L1. You can do a one-var stat. You can find out the range. How do I know the range? God bless you. How do I know the range? Good, the highest from the lowest. Max minus the min. Do I find the max when I do the one-var stat? Yeah, just scroll all the way down. Scroll all the way down, you find your max, you find your min, subtract it. My mean, this is my x bar. What's my rule for the decimal? One more place than the data. So the data has no decimals, my mean has one more. Make your standard deviations match that. Since this is a population for each American conference team, so that means I'm using all of them. This means this is a population. This is important that you know this. So I have to use the O X. This is the sigma X. O for population. DO. If I need to get to my variance on my calculator, because remember when we do the chart, this is why I like you to think about when we do it. When we do the chart, we do the variance first. Our variance is the sum of the squares divided by n. And then, to find the standard deviation, we take the square root. So our calculator is backwards. They give us the standard deviation, so we have to go reverse this. So we square the standard deviation to get to the variance. So in your calculator, you can go to VARS, come down to number 5, click on your standard deviation, and then just say square. Oops. I don't know why. Number 5, click on standard deviation. Let's try it again. There it goes. And square. Now, I don't have anything in there, so it didn't find anything. But what happens is this. Remember when we did this? Sometimes after we divided this out, we got a nice number. So say we got 50, or 49, well, the 50, or 48, or something like that. When we did the square root, it was an irrational number, or decimal. If you square a rounded number, you will never get back to the true number that was there. So that's why you have to use the calculator to do that. Your calculator will get back to it. So everybody can do that? Did I give you 14? No. What was the next one I gave you? 15. So everybody can do this? What's the difference between this one and 13? It's a sample. So everything else is going to pretty much work the same. I'm still going to put this in my L1. I'm still going to do one var stat. Just by the way, we never in this course use two var stat. Even if you have a frequency table, it's still a one var stat, one variable. The variable that I'm measuring here is the ages. So I'm only having one variable. If I use a frequency, I will say L1, comma L2. We never use the two var stat. So tell it what thing you put it in. Again, find your max minus your min. You can find your range. This time you're using your SF, your sample standard deviation. Are you doing a snow dance back there? Miss Venable had a saying, she used to say, if you wanted it to snow, you wore your pajamas inside out or something like that. Yeah, Miss Venable?
No, I used to.
You did that too? Really? You put your pajamas inside out?
I used to do that.
That's cute. That's cute. Okay, so a couple of you called me over on this one. Take your book and turn it sideways. Turn your book sideways. I don't think I can rotate this. No, I can't. If I'm on the smart board, I can. On the smart board, you can rotate it. In Word, I can't rotate it. Now, just turn your book. Look at this like a frequency chart. Isn't this like all your 13s, all your 14s? Look at your frequency. This is a lot wider, isn't it? Which one is more narrow? This guy. So which one should have the smaller standard deviation? This one. Okay? And then if it's wider, there's more variability. That's all that means. You're further from the mean. You have more variability. Think of your test scores. If your test scores tend to be 80s and 90s, you're closer to that mean. If your test scores are all over the place, 50s, 60s, 70s, 80s, 90s, your mean is way in the middle of that, and your test scores are spread out like this, right? Don't you vary from that test score a lot? Whether you get a 50 or a 90 and your test score is a 75 average, yeah, you have a lot of variability. So the closer to the mean, the less variability, the smaller the standard deviation. 19. I know a lot of you got stuck on 19. All you have to do is just think of this problem. So you're applying for 2 jobs. Sarah, you go to company A. They have a mean average of 31,000 with a standard deviation of 1,000. So let's just look at that for a second. Here's your 31,000. So you can go 32,000, 33,000, 34,000. 99.7% make between this and 34,000. If you're going to this company, are you more likely to get an offer of 33 way up here? Where did most of the people get? Right in here in the middle, right? Or a new person, where is a new person most likely to get? Are they likely to get the highest salary? Probably over here somewhere even, right? So 34 is really kind of out of that area. The second one says, same mean, 31,000, but now your standard deviation is 5,000. So this puts me at 36,000. This puts me at 26,000. Where is my 33,000? Right in here now, isn't it? It's closer to the mean, closer to the average. I'm a new employee. You think they're going to pay me big bucks when I come there? If I'm good, maybe I have a lot of experience, they might pay me a little bit more than the mean. That's how they get you there. They'll say, well, our mean is 31,000, we'll give you 33. But will they give me 33 when half of these people, 95% of these people, make less than that? Huh. So which one are you more likely to get? Okay, so if you just kind of think of it that way, make sense out of your standard deviation. We do a lot with standard deviations here. 21? Yes. It was the one with the 5,000. You're more apt to be closer to the mean there, right? The 33, you're too far away from the mean.
Yeah, I mean, sometimes they know what means.
Yeah, no, I'm sorry. I thought I kind of, yeah. It would be more likely with the higher standard deviation. So these guys, think of what we did yesterday. This was our mean. All the means are smack in the middle here. Here's my graphs. Which graph is the narrowest graph? 3. So should that have the smallest standard deviation or the largest? Smallest. Because it's the closest to the mean, right? They varied less. They didn't vary far off the mean, right? They don't have a lot of movement out this way. Which one has the largest standard deviation? 2. Look how far away that is from the mean. And this one would be the middle guy. Okay? Stop me if you have any questions. Again, just another way to look at it, at a dot plot. A dot plot too looks like a frequency thing. Kind of build yourself around here. These guys, all your means are exactly the same. All your means are the same. This from here to here, a little bit more variability in right in here. If we took these out, they would pretty much be the same and put them up here. But these are spread out more. So this one is the furthest spread. This one is the smallest standard deviation. This one is the medium, and this one is the largest. Okay? They almost look the same, those two, but there were 2 points that moved up in the other one. So where did they move, these 2 points? These 2 points move closer to the mean. Closer to the mean means they're going to have less of a standard deviation, right? Standard deviation is how much you deviate from the mean. Think of what the definition means. Empirical rule. I know you got, oh, Sarah. You do need to do that for sure.
Oh, wow. Santa must be fun.
Yeah. Either that or they're going to cancel Halloween again. Remember a few years ago when it snowed and they canceled Halloween that week? Okay. Did everybody get this part? Putting it on the graph? Okay. Again.
Very good.
Watch. You're going to start like this. Are you guys writing this down if you don't have it?
Oh, I'm sure
I hope so, because this is what you have to do. Your mean goes here. 67. This is your mean. Sarah, you got this? You have a standard deviation of 4. That means every standard deviation you move away from the mean is 4 away from it. So this is going up, because these go in order, from lowest to highest. Lowest to highest. So add 4, add 4, add 4. The opposite way, just subtract 4. These have to make sense. From 55 to 79 they go. Now, estimate the percent of the vehicles that are between 63, that's this guy, and 71. What does your empirical rule say for plus or minus 1 standard deviation? 68%. 34 each side.
You, like, if we have this on a test record, you provide us with the chart, we have to memorize it.
I would provide you with a chart. I kind of like you to get used to the plus or minus 1, plus or minus 2,
Yeah.
plus or minus 3.
I'm saying you provide the
I do.
percent. Okay.
I do. I will give you the chart.
And will we ever get it where it's like, say, 0.5% off, or is it always going to be a whole number?
Well, we will, but we're gonna find those areas differently because we're gonna use table 4. We're gonna use a different method to get there. So that's why we do a generalized one. Yeah. Yeah. So when you lay these out and you look at these x values, what standard deviation is this? 1 down, 1 up. So this whole area, it's a symmetric graph. So this whole area is plus or minus 1. 1 down, 1 up. That's why we say plus or minus 1. Plus or minus 2 is from here to here. So plus or minus 2 goes from 59 to 75. And that tells me 95% of my vehicles will be between 59 and 75 miles per hour. So if I'm sitting there on the road estimating what they would be, I would find 95% of my vehicles are going to go between those 2 speeds. What this is a good forecasting tool. So say, ladies, that all of a sudden I want to say, well, the next 100 cars, what do I estimate them to be? I don't know. But since I did this, and I could say, well, I found 95% of them were from 59 to 71, I'll take 95% of 100, which is 95 cars. I expect 95 cars out of those next 100 to be between those 2 speeds, which is why we look at these. Okay? Everybody okay with this?
Yes.
Between what 2 speeds? Between what 2 speeds do I have 99.7% of my data? Between what 2 speeds? 55 to 79, plus or minus 3 standard deviations. Good. Your empirical rule just kind of generalizes it. Did I give you 30? Okay, 30, we do the same thing. They just ask this a little differently. We put the mean in the middle. There's your 70. Your standard deviation is 8. Add 8, add 8, add 8. Subtract, subtract, subtract. Now, between what 2 values does 95% of your data lie? 95 is between what 2 standard deviations? Plus or minus 2. So I look between this one and this one. I look up here and I say from 54 to 86. Okay. lies 95% of my data. It just asked it reversed. Okay? Now this is a good thing too. From example, did I give you 31? Yeah. Okay. From example 31. Example 31, remember we found 68%. Say I'm going to use the 68% and I have a sample of 75 cars coming through. The next 75 cars. And the next 75 cars, my boss calls me. I'm a trooper on the road and I'm looking for speeders. And I found that 68% were going between, God bless you, between, what did we say they went between? 59 and, what did we say? Let me just move this up one second. Between 63 and 71, right? Between 63 and 71. So I say I got about 75 more cars coming through. How many of those 75 do I expect to be between 68 and 71? 68%. 63 and 71, 68% of them. So I just multiply this, and out of those cars, I will expect 51 to be between those two speeds. Because that's my percentage. Okay. In a sample of additional 25, how many of those 25? 68% of those 25 I expect to see between 63 and 71. Okay. It's a good forecasting tool. Give me the percent. That's why we look at percentages. Does this make sense?
Yes.
Chebyshev's theorem is a little bit different. Chebyshev says this is not a normal curve. You have a skewed curve. I really can't use the plus or minus 1, plus or minus 2, plus or minus 3 because it doesn't fall symmetrically. But I still need to set this up so that I can see what numbers I'm looking at. And then I'm going to find the standard deviations and use his formula. So it says you are conducting a survey on the number of pets per household in your region. From a sample n equals 40, the mean number of pets is 2, the mean goes in the middle, and the standard deviation is 1. So I set up my chart as if it were normal. Add 1, add 1, add 1, subtract 1, as far as I can go with 0. I can't have negative pets, right? So now I want to determine, using Chebyshev's theorem, that this is not a normal curve, between 0 to 4. 0 is at what standard deviation? -2, and 4 is at what standard deviation? 1. This is my mean in the middle.
2 was your
Nope, 2 is my mean. That's because you were talking. You were snow gazing.
4.
So that's the 4, 2. So what is k equal to? 2. That's how many standard deviations I am off the mean. Shh. Guys, this is important. You have to use your concept of your normal curve to find out what k is. If it's plus or minus 2, k is equal to 2. If it's plus or minus 3, k is equal to 3. There's only two things it can be, a 2 or a 3. So we substitute this into his formula, and we find out 75% of the households studied will have between 0 and 4 pets. So if now I'm looking at 40 households, 75% of those 40 I estimate to have between 0 and 4 pets.
I did it without using like all that work on the right, and I still got the answer. Do I have to show the work for it?
Well, you have to show me that you substituted this in. You just knew the 2 was 75%.
Yeah.
Yeah, but you just have to show me that you used the formula. It's only going to be two things, either the 75 or the 88.9. Okay? Here's another Chebyshev's. Now this one answered a little differently. The mean score is 88. So build this. Here's my mean. With a standard deviation of 4. Go 4 up, go 4 down. Okay? Using his k equals 2, interpret the results. So I stick k equal 2. I don't know what he wants me to say yet. And I find that 75% of the data lies between plus or minus the 2. So where am I at? Between 80 and 96. between 80 and 96. Just another way to look at it. Okay? This is the only time we use a non-normal curve. The only time is Chebyshev's theorem. Some guy that came up with this design. But again, look at how broad his still is. Plus or minus 2. Ours says 95. He says 75. So he can't be as close to us, you know, because it's not, we don't know where the skew is. But he has a way of just estimating. Did I give you 39? No.
No,
I give you 41?
43.
43. 43 and 44. This is important. This is your coefficient of variation. Your coefficient of variation is the one thing that can help you compare two unlike data sets. We're going to find out z-scores do the same, standard deviations do the same, but right now we're doing coefficient. The coefficient of variation is just a ratio between the standard deviation and the mean. So therefore, we have to find the standard deviation and the mean of each one of these. And what keyword do we need to know? Sample, because that makes us use our S, not our sigma. So we find our two pieces of information. Use your formula. Your formula says, take the standard deviation, in this case the sample standard deviation, and put it over the mean. And you got to figure, you got to do the smaller divided by the larger, because you're going to multiply it by 100 and come out with a percent. A percent should be under 100, right? If you did it the other way, you would have a humongous percent, which can't happen. So divide it, multiply it by 100. Now we can compare it. The higher the percent, the more variability. Okay? So New York salaries have a higher variance. They vary more than Dallas salaries. And how does this help you? Let's say you're going to look for a job. And you look for a job and you say, well, New York has a bigger difference in salaries. If I go to Dallas, they're closer to the mean there. So maybe I want to go to Dallas and be closer to the average salary. Not a lot to find in this, but this does have a way that we can compare two data sets. Okay? Good? And the last one, right? It's the same type of thing. Again, what key word is up there that we need to remember? Sample. Because sample tells us Sx, not omega x. Not sigma x, sorry, sigma. We find those, and again we compare. Boston salaries are higher in percentage of variation, so they vary more than a Chicago salary would vary. I'm going to